Okay. Let me just introduce some notations. So I will denote. So this bit I will denote as the plus OXI. That's a Fourier transform of the normal derivative of the field on the surface of. So it's on the surface of our scatterer for the symmetric problem. This thing I will call U minus. And it's other way around. Sorry about this. This is V minus because I integrate from minus infinity to 0. There's just a mnemonic way to think about it. And this is called a minus function, this is called a plus function. And yeah, okay, and this even though it might actually go, probably makes sense. Okay, say and rewrite my equation like this. Yeah. Just be careful with the signs. So here V minus is without the sign. And yeah, I think I will put minus here, so this is kind of minus KT. So this is some algebraic equation, and this equation has two unknown functions. So like by default, we don't have a unique solution to this equation. We don't know what is V minus, and we don't know what is V plus. And we know what is K and R. And this thing is called the kernel of Wiener-Hopf equation, and this is the forcing of just right-hand side, the inhomogeneity of our equation. But since this is a half line or like one-sided Fourier transforms, we know some analyticity properties of these functions. And I call them minus and plus not only because I integrate from minus infinity to 0 and from 0 to plus infinity, but also because I can say something about them. And what things I can say? That V minus is analytic in lower half plane. So is it clear for you why it's analytic in lower half plane? And maybe I can ask a simpler question. Why is it clear what problems we will have in upper half plane? Yeah, the integral does not converge, and then we don't know what do we have there. But in the lower half plane, this integral converges exponentially, and that's actually the only requirement you need for analyticity. There is like a theorem, but you can do it formally. So, like you have a convergent integral, and then you can establish analyticity in each point if you have convergence. And for the same reasons, U plus is analytic in upper half plane. And it's actually slightly more than upper half plane and slightly more than lower half plane because we have a limiting absorption principle. I forgot to put this part, but because of the limiting absorption principle, we have our spectral variable, complex plane of our spectral variable. And just by studying the asymptotic behavior of the scattered field, we know it should decay exponentially, and the exponent will be linked to the imaginary part of the wave number. Like it will decay as exponent and something like this. And that's why for one function we have uniticity region like this. So for upper function it's like this. And for lower function it's like this. And this line is just if you open or novel, he discuss this part and he a bit more precise because we also can have a pole and this pole can be between. So sometimes we can have a pole here. So for one of the functions, the strip can be shorter. But like the key point that analyticity domains of two functions, they overlap, and that's important. So we can build a function analytic in the whole complex plane out of them, and then we can apply Lewis theorem. And what else do we need to know to apply Lewis theorem? We need to study the behavior at infinity. And we do it using Watson schema. And we do it the same way we did it for this, with the Sommerfeld solution, and I will just write the answers. So V minus behaves as in open half plane, and U plus behaves as in upper half. So both functions decay at infinity. And this behavior will allow us to apply Lewis theorem at the end. So what else do we know? So what can we say about our kernel? So I didn't start to solve the equation, I just discussed the analyticity properties of functions we have here. Once we understand them, it will be quite easy to solve it. So our kernel is like this, and what what can we say about it? It has two branch points.
So we can write
One here, one here. So they have small imaginary parts. That's why they are shifted from real axis. And that's it. I can, as people usually do, I can draw some cuts points from them. And for our right hand side, it's just a pole. But we need to figure out where this pole is located. And that bit is quite important for solution, because that will affect how we solve the problem. As I said, cos theta is negative, because it's from pi over 2 to pi. So our pole lives somewhere here. And I will call it psi m to make things short. So this function is analytic in upper half plane and has a pole in lower half plane. It's a quite simple function. So, and we are coming to the climax of our lecture. We are going to solve the equation. So, I don't remember everything. Step 4, solution. Solution is done also in 3 steps. So we have A. We need to factorize the kernel. Factorization. Of K. So, what do I mean when I say we need to factorize? It means we need to do what is known as a multiplicative factorization. So we need to present K as a product of 2 functions. One of them analytic in upper half plane, another one analytic in lower half plane. So, do you have any ideas what is K plus and what is K minus? I'm waiting for your...
Can we use like difference of 2 squares as well?
Say again?
Can we use like difference of 2 squares?
Difference?
Like split the
Yeah, we split it as...
like K plus.
Okay. Understand.
Okay, say, what is K plus? Make you guess.
K plus the sign.
Yeah, what is K plus side?
Like the like square root of K plus K plus the what is this?
K plus side.
Yeah, that's
I just okay.
sorry, I always forget this.
Yeah. So you forgot the name of the letters.
Yeah.
I'm sorry. That's how I write down side. I cannot do it nicely.
Yeah, I write it the same, but I always forget.
Yeah, it's side. And I also will put this constant here. Just it doesn't matter, but I need to put this constant somewhere. obviously K minus is like this. Good. So now we divide the equation by K minus. I write down probably partial some details. This equation. So now we have some nice things. This bit is analytical, this term is analytical in lower half plane, because this thing is analytical in lower half, and this thing is analytical in lower half plane. Actually, when we do a factorization, there is a second requirement. These factors, they should not have any zeros in their half planes. Otherwise, when we divide, this thing will have zero and our procedure will fail. Like to be honest, the procedure will not fail, but then we will be required to do some additional steps. We will do some pole removal. But here, there is no zeros, we can just divide, no problems at all. And this function is analytic in upper half plane. But this function is analytic, so this term is analytic in lower half plane, but this term is analytic in upper half plane. So we need to do additive factorization of this term. It's because weird, but this say one, it lives here. So we are coming to step 2. Yes, step B. Yes, sub step. Substep B. Additive factorization. So we have this thing, I will call it prime. Divided it's different from our previous calculus. And what I want to achieve is the following thing. So, do you have an idea? Like it's actually in general it's quite messy to deal with a branch point, but it's quite easier to remove a pole. We just need to subtract it. So we can subtract the pole. And then we will get a function which is analytic in lower half plane. Let me write it down. How I subtract the pole. And this is technique is known as pole removal. the idea of course is similar. So this is just my right hand side, modified. And now I subtract or add here the following term. This is just a polar function. And this function doesn't have a pole here. Because when we will take a limit, this thing will kill this thing. So we will have 0 in denominator and also 0 in numerator. And then by taking a limit, we will obtain a continuous function at this point. Is it? Okay. Right? And but this bit, it's analytic in upper half plane, and since we subtracted it, we need to add it back. So our factorization is add the same term. Profit. So we did it. And then final step towards the solution. Is to apply step C. Why? I need my notebook because I never know how to spell UV. Because a tough machine, you will scared. So, do you know what is Liouville stereo? You don't know? No, Liouville stereo. I mean, it's terrible, but we will fix it. Liouville theorem says that if we have a function, analytic or galomorphic, everywhere on the whole complex plane, then this function is constant. Believable? Believable. So you know it, I suppose.
I've heard it, yeah, but not with that name.
Yeah. So function analytical everywhere and decaying at infinity. So like a general theorem says, if you have a function analytical everywhere, this function should be a polynomial. And polynomial grows at infinity. And if this function decays in infinity, this function is a constant. And let's construct such a function. From what we have. We have just arranged terms in our Wiener-Hopf equation. So this is just our equation. But we arranged our terms in the way that this bit is analytic in lower half plane and this bit is analytic in upper half plane. And then I do a conceptual step. not me, but Wiener-Hopf, somebody does. They say, okay, let's define a function f, which will be equal to this in lower half plane and to this in upper half plane. Thus, we defined a function which is analytic everywhere. And also, we know how this function behaves at infinity. We have our growth conditions, and these two things we just know. So if you look, you will see that this thing decays as psi minus 1. And this thing also decays as psi minus 1. Thus, our conclusion that f of psi is 0. It's constant, and this constant is 0 because we have an exponential. Well, not exponential, but terminal decay. And that's it. We have our solution. And actually, to build the whole solution, it's enough to find u plus. We can also build v minus, but we don't need it to cover the whole solution. And then write it down so you will have it. And this thing is a Fourier transform of the scattered field on the half plane. That's how we define it. So what do we have? We know the field and its normal derivative on the half plane. Then we can use Green's reconstruction formula and recover field everywhere. So we know, I will put it in my notes. So we know both U scattered and U scattered again on half plane. Where this thing we know from boundary conditions, and this thing we just computed. So this is non-trivial part of the solution. And like formally I can write it like this. I mean the reverse Fourier transform. So we know this. You can use Green's reconstruction formula, which we studied a couple of lectures ago, and we will have field everywhere. And I did it because I'm not lazy. And I will give you the solution, and then it will be your task to check that I obtained it correctly. And that's not hard, it's just some computation. So, and also you can compare it with the solution we obtained using so much field integral. All the fields everywhere is, of course, if I'm not mistaken. I tried to be precisely. And you know, we can have a look at this expression, and this expression looks quite believable because this is, of course, some plane wave decomposition. So we have a plane wave, and we have some term where we integrate this. And what's the interesting bit? So, yeah, okay, that's probably the end, and there will be a hypothetical homework. Which is just part of the discussion, like things which are useful to think about. Like, first of all, you can obtain it yourself if you wish. That's a useful exercise. So there are many ways to obtain it, and I will give one way, a tip, like a general approach. So as I said, we apply Green's reconstruction formula. We have our half plane. For Green's reconstruction formula, we have Green's function. And what is our domain? Our domain is, just an ugly circle. Domain is like this. And also the same domain we use to obtain this reconstruction formula. And we choose as our pair, we choose use scattered. Yeah, use scattered. And G. Where this is LS. We apply Green's theorem with these two functions in this domain. And of course, the integration of this big circle will go to 0, and this thing will give value of our scattered field, and then we will have some convolution type or integral with Green's function. Then the final step is to use plane wave decomposition for Green's function. We are playing this plane wave decomposition at lecture 1. And then plane wave decomposition will give us something like this after some algebra. Like, you can try to see it first. And of course, point B is compare to Sommerfeld, and more formally prove that this expression is equivalent to this Sommerfeld solution, because this expression looks similar, but actually it's quite different. So it's, we have some exponents in the denominator. So you need to play a bit with it to show that it is the same expression. It's equivalent. And estimate scattered field in far field. as r tends to infinity. So find the saddle point asymptotics. Of course, you suppose that r tends to infinity, and then you can apply saddle point method. And you will have a directivity of the scattered field somewhere, and a plane wave if you have a reflected wave in your solution, but whether you have a reflected wave or not will depend on angle of observation, because a reflected wave only exists, if it's like here, reflected wave will exist only like here. And will not exist. And here you will have just the scattered field, so it's like a shadow zone. So you have some geometry here, and you can study this geometry through asymptotic estimation of the symmetry. Like, try to do it and see where this pole contribute or not contribute to the solution. And it depends on the angle. Okay, I think that's it. Thanks for your attention. Do you have any questions? Good, good. So I take it that you understood everything. So, okay, see you next time. Don't forget to like, share, and subscribe.
And hit the bell.
And hit the bell.